Hello students, welcome back. We're going to continue today with this is going to be a continuation of where we left off last. Signal transduction part 7. And I wanted to add one thing to signal transduction before we left the beta 1 adrenergic receptor. And so let's create a really rough drawing of our cardiac cell. But this time it doesn't have to be a cardiac cell. It can be any cell. So let me get some swatches here. So I'm just going to draw a cell here. Okay. We have a cell, and in that cell we're going to have a membrane. I mean, not of course that's a membrane. We're going to have a receptor. And this receptor, let's call this our beta 1. This will be the beta 1 adrenergic receptor. So for now, let's not call this a heart cell. So 1, 2, 3, 4, 5, 6, 7. This is our, let's call it our, it can still be, well, let's just say this is an adrenergic receptor, not beta 1. So for this example, this is going to be an adrenergic receptor in our large intestines. It's going to be an adrenergic receptor in our large intestines. Now what's going to happen? What happens here? This beta, what type of protein is associated with this? Let me get this. I wonder if I get that color back. Nope, I can't. Okay, and this has this on it. Does anybody remember what type of protein is associated with adrenergic receptor? A G protein. So I'm going to write here, I'm going to put, this is going to be alpha for our G protein, and then we're going to have beta and gamma. Okay. And now when the alpha is active, what's going to be attached to it? GTP. Okay. And actually, I want to put mine on different layers. You all don't have to do this. I want to make alpha a different color. Okay. And so here is my alpha, and it has GTP. Okay. Also on G alpha, there is there are these scissors that clip the GTP to make GDP. What do we call that part of the alpha? What type of activity do those scissors have? If they can clip off the phosphate off of the GTP. Right. This is our GTPase activity. It clips off one of the phosphates, and then you come back to GDP. Make sense? Right. This is a GTPase. So this is our GTPase, and it's on the alpha. Now, you don't want your alpha to be active all of the time, because if your alpha is active all of the time, then you're going to activate. I'm going to draw these very crudely here. You're going to activate. I'm going to zoom in on here. What protein does G alpha activate? Adenylate cyclase. And adenylate cyclase makes what metabolite? Cyclic AMP. Cyclic AMP activates protein kinase A. And then protein kinase A leads to whatever the response is going to be. And since we say this is an intestinal cell, that response is going to be opening some chloride channels, pumping out chloride, And following that chloride, we're going to have a lot of water going out. So this is an intestinal cell. Question. Oh, the adenylate cyclase, adenylyl cyclase. This is the protein it activates. Remember, it activated that protein in the heart too. Y'all remember that? So the G stimulatory alpha activates adenylate cyclase. That produces more cyclic AMP, activates protein kinase A, and then that leads to a response. In the heart, that response is greater contractility. But in this intestinal cell, it's going to be chloride efflux. It's just going to push out a lot of chloride out of the cell. But then a lot of water is going to go out of the cell. Okay. Yes. This is an intestinal cell. The whole point of this is to get to this step, this stage right here. There is a toxin. There is a toxin that you can... Okay, I'm going to ask you all this question. Okay. What would happen in this cell? I want you to think about it for 5 seconds first. What would happen if you could block the GTPase activity of the G stimulatory alpha? Again, this is the question. What would happen if we could block the GTPase activity of the G alpha? Okay. Think about it for 5. Does everybody understand the question? Okay. Think about it for 5 seconds. Does anyone have the answer? Anyone think they have the answer? No. What was that now? It would lose too much water. The cell would lose too much water because if you block the GTPase activity, that means GTP is going to stay on G alpha all the time. And it's going to continue to activate adenylate cyclase. If you continue to activate adenylate cyclase, you're going to have lots of cyclic AMP. If you have lots of cyclic AMP, you're going to have a lot of protein kinase A activated. If you have a lot of protein kinase A activated, you're going to open a lot of chloride channels. Lots of chloride is going to go out of the cell. Lots of water is going to go out of the cell. Exactly. That person is going to become dehydrated because what's going to happen, all of that water is going to go into that person's intestines, and that water is going to pass out through their digestive system. It's going to pass out, and that person is going to have extreme diarrhea because they're going to lose all of that water, and they're going to eventually, if they're not treated, they're going to die of dehydration.
So if you take something, like if you take like ammonium or something like that, does it have like something in it to block? Is that how it works?
Ammonium, exactly. Ammonium stops diarrhea, so it's going to block that. It's going to block that. Exactly. You're going to, if it works by this mechanism, what it's going to do, it's going to actually have something that can clip the GTP to kind of turn it off. I don't know the exact mechanism of ammonium, but you're on the right track. Your thinking is right. Okay. Does everybody understand what the disease is? This is a disease. This is a pathological condition. The GTPase is not clipping off the GTP, so G stimulatory alpha is staying on too much, and it ends up with your intestinal cells losing too much water in the GI tract, and too much water is going out of the body. That's the pathological condition. Extreme diarrhea. Now what I'm going to do, now that you understand the mechanism, I'm going to tell you the name of the toxin here, and then I'm going to tell you the name of the condition. Everybody okay? See, the name of the condition and the name of the toxin, those are really, they don't matter that much. What matters is the mechanism that you already understand. Everybody okay with that? Exactly. Right. It's the the G stimulatory alpha with GTP. That's the active one. And so in your heart, to prevent your heart from beating too fast, this thing has GTPase activity. It clips it off. It activates adenylate cyclase for a while, but then it clips itself off to turn itself off. But there is a toxin that blocks that GTPase, and it stays on all the time. So it's producing lots of cyclic AMP, and you're releasing lots of water out of those intestinal cells. You're going to have extreme diarrhea, and you will eventually die of dehydration. Everybody understand the condition first? Okay. What do you want to know first? Do you want to know the name of the toxin first, or do you want to know the name of the disease first? Okay. The name of the toxin. Okay. Even though you all want to know the name of the toxin, I'm going to tell you the name of the disease first, because you all already know the name of this disease. Sometimes when you go to Mexico or some Central American countries, they'll tell you don't drink the water, because if you drink the water, you'll get extreme diarrhea. You'll get this condition that causes extreme diarrhea. What is the name of that condition? Cholera. Exactly. That's what the extreme diarrhea is. That condition is called cholera. Okay, so let's write that here. Excellent. Excellent. I knew you all would come up with it. So I'm going to put up here cholera. Cholera. Now, the name of the toxin, wow, is going to be almost too simple. So let's go. I know what I'm going to do. I'm going to put like some gel cells here. I'm going to like put this GTPase in gel.
The cholera is caused when there's not any GTPase.
There's no GTPase, exactly, because the toxin has blocked the GTPase. Now G-alpha GTP is on all the time, and that's going to lead to a loss of water. Okay, let's put ourselves a gel cell here. Okay, I'm going to put the name of the toxin right here. Okay, we're putting the GTPase activity in gel, so it can't do anything. Make sense? Now, if you had to come up, let's say we go to a 5th grader or a 5-year-old, and we say we have this disease. This disease is called cholera, 5-year-old person. We need for you to come up with a name for the toxin that causes this disease. What would that 5-year-old person say? What would that 5-year-old call that toxin that causes cholera? Cholera toxin. Exactly. That's the name of the toxin. Cholera toxin. Okay? And that's how you get the disease cholera. There's a bacterium. I can't remember the name of it. Bordetella. I think it's Bordetella is the name of the bacterium. And so when you drink this, it has that bacterium in it, and then that's what gives you cholera. Make sense? And this is going to happen in the digestive tract, which makes sense. So in intestinal cells. Let's go next to another. Let's look at another condition. Okay. Actually, I should have put all of that. See, I should have put all of that in a. Let's see here if that wants to do right. Okay, give me 1 second here. I'm going to actually put all of this in one folder here, so I can get rid of it as I want to. Now, this time, we're not going to be in the intestines. We're going to go somewhere else now. So I'm going to block all of that. Let's go to the lungs. Let's go to the lungs next. Okay. Now, I'm going to draw a lung cell. A cell that may be found in the lungs. Okay. here's a lung cell. Now in this situation, in the lungs, we actually have an acetylcholine receptor. It really doesn't matter what receptor it is. 1, 2, 3, 4, 5, 6, 7. But now, is this receptor, if this is an acetylcholine receptor, is it a muscarinic receptor or a cholinergic receptor? What'd you say? Muscarinic, exactly. Because if it's muscarinic, it's 7 pass. And if it were a nicotinic cholinergic receptor, it would be an ion channel. Okay. And so in here, we don't have G stimulatory, we have G inhibitory. So I'm going to put here this one. I'm going to put my G, I'm going to put my beta inhibitory and my gamma inhibitory. And now we're going to have, I'll put this on another layer. We're going to have G alpha. This is going to be alpha inhibitory. And alpha is going to have GTP when it's in its own state. Okay. Now what's going to happen here? We're going to have adenylate cyclase here again. So here's adenylate cyclase. Adenylate cyclase is in the lung cell. So this is in a lung cell. Adenylate cyclase is going to lead to, if you have lots of adenylate cyclase, that's going to lead to more cyclic AMP. That's going to lead to lots of protein kinase A activity. And then that is going to eventually lead to your physiological response. Physiological response. Now, if you have too much adenylate cyclase activity, you're going to have too much cyclic AMP, too much protein kinase A. You're going to have too much of a response in your respiratory system, and that's going to cause you to cough a lot. Cough. That's what a cough is. It's going to cause you to cough a great deal. If you have too much, adenylate cyclase activity, you're going to have too much cyclic AMP, too much protein kinase A, and you're going to start coughing excessively. But one good thing about this is prevented. This is prevented because here you have the alpha inhibitory GTP actually goes and it blocks adenylate cyclase. It lowers the activity of adenylate cyclase, lowers cyclic AMP, lowers protein kinase A, and you don't cough. You just breathe normally. Okay? Does that make sense before we get to the disease? No, see, if you didn't have this parasympathetic situation with alpha inhibitory, then the physiologic response would just go wild. It would be on its own. You'd have too much adenylate cyclase, too much cyclic AMP, too much protein kinase A, and then your respiratory system would start coughing too much. That's if you didn't have this acetylcholine and its receptor here. That's if you did not have this. And so acetylcholine is going to bind here. So when acetylcholine binds, it keeps the respiratory system in check. It binds, your acetylcholine binds to the muscarinic cholinergic receptor, that turns on the alpha inhibitory. Alpha inhibitory goes to adenylate cyclase, lowers its activity. That lowers the amount of cyclic AMP, lowers the amount of protein kinase A. Now you don't cough. Now the respiratory system is not on too much. Make sense? Normally in the respiratory system, you're supposed to inhale and exhale. But if it's out of control, you're going to start coughing too much. You seem perplexed. Okay, very good. Now, does everyone understand the situation before we talk about the biochemical mechanism of the disease? Okay, very good. Now, the question for you is, what would happen to an individual? Okay, let's do it this way. What would happen to an individual if we put all of this in jail? If we put, well, not even put that in jail. Or what if, here it is. Okay, I'm gonna make a copy of this because I need to explain this. So let's put this to the side for now. I'm gonna put, because this does, in this disease you don't even have this, so I'm gonna move this over. I'm going to do this. I'm going to just make a copy of it and hide this one. Now we're going to go back to this one. Okay, what's going to happen in this disease, I'm going to get rid of GTP, and you're going to have, I want another color here, you're going to have GDP. So now there is a toxin. Okay, let me just ask you this question. What would happen to an individual if they were not able to convert this GDP in this situation? They couldn't convert this GDP into GTP. Okay? Oh, don't answer it yet. I want you to think about it for 5 seconds. Okay? Again, what would happen to an individual if they were not able to convert this GDP, which keeps the alpha inhibitory blocked all the time, or in an inactive state, to GTP? You could not convert GDP to GTP. Okay? Think about that for about 5 seconds. 1, 2, 3, 4, 5. I think it was you that was answering it early. Say that again. Exactly. This person would cough all the time because there would be nothing ramping down your respiratory response. And that person would just cough excessively. Does that make sense? Now, do you want to know the name of the disease or the name of the toxin? The toxin, okay? We're going to name the disease first, however. So let's do this. Okay. So here we have, now what happens when you have GDP bound, you have alpha, beta, and gamma all together. And there is a toxin. There is a toxin that blocks all 3 of these. It puts all 3 of these in jail. Okay. So here we have a toxin here. And it puts all 3 of these. It locks these 3 together. So I'm going to lock them together too. So they can't get apart, and you can't convert GDP to GTP. Okay? Now, let's get to the disease first. Sometimes in babies, and there's a commercial on this about this right now. Sometimes in babies, they'll have this condition where it's almost like a form of whooping cough. And the babies are just coughing all the time. Does anybody know the name of that disease? Pertussis. Exactly. The disease is pertussis. Okay? The disease is pertussis. Exactly. So these babies are just coughing excessively all the time. And now, let's say we go to that baby and we say, baby, you have a disease. You have a disease. And it's caused by a toxin. But we don't know, we don't have a good name for this toxin, little baby. In between your coughs, can you give us a name? What would that baby say? What would that baby call that toxin that causes this disease? Pertussis toxin. Very good. Very good. And so that is the toxin. Pertussis toxin. Okay. And that's how pertussis toxin works. Does it make sense?
So pertussis toxin keeps the GDP from becoming GTP.
Exactly.
Block the AC.
Exactly. See, with the pertussis toxin, keeps the G protein off. Cholera toxin keeps the G protein on. So you can think about it that way. I really wanted this to be on test 1 because it just, but that's okay. I mean, you have plenty of opportunities to learn those things. Okay. Okay, I think we're going to have to. Any questions? Any questions about what we've talked about today? Okay, no questions. Everybody understands everything okay? Pertussis, cholera. Right. It keeps the G protein off, but since it's an inhibitory G protein, whatever response it was turning off stays on all the time. Okay. So let's do a little review then, since you don't have any questions. Let's go back to this one here. Now here with cholera toxin, here we have an adrenergic receptor. So what could bind that adrenergic receptor? What kind of substance is going to bind here? What binds to an adrenergic receptor? Epinephrine. So what's going to happen here, when epinephrine binds in your GI tract, what's going to happen is going to activate this G protein. And if cholera is there, you just ingested something. You drank some water that has it's Bordetella and that's pertussin. Vibrio cholera is for cholera. Yes. And so you're taking some water that has, it doesn't matter, this bacterium in it. That bacterium is going to release this toxin, and that toxin is going to block the GTPase activity of your G protein. So this G protein is going to stay on all the time. So you're going to have an excessive activation of adenylate cyclase, excessive cyclic AMP, excessive protein kinase A activation, and then you're going to have a great loss of chloride ions followed by water, and so your large intestines are going to be filled with water, and that water is going to pass out of your body, that's going to cause extreme diarrhea initially, but end up with dehydration. Make sense? Oh, yep. You have to be careful. Yep, you have to be careful. But now you know, in conditions like this, the treatment, I don't know exactly what they would use. Well, they could use antibiotics for the cholera, but the thing is, the toxins are, what is it? It's not like gram-negative bacteria. Gram-positive bacteria release their toxins. And so these toxins, they aren't living. They're just proteins. And so you need something to actually block those proteins. And usually you'll use an antibody to just go in, bind to the protein so it can't get to the GTPase. Does that kind of make sense? You'll learn more about antibodies in immunology. Okay, let's go. And then this one here, pertussis. A baby coughs a lot. Why? Because some kind of way the baby, sometimes if the parent has has the bacterium, they can pass it on to their child. And what happens if this bacterium gets into the child again? It's going to release this toxin. This toxin is going to lock those G proteins together and won't allow GTP to come. So this G protein is going to become inactivated. Now this G protein can't go and inhibit adenylate cyclase and ramp down your respiratory response. And so this baby's just going to be coughing all of the time, And it can make the baby tired and make it hard for the baby to breathe, because if you're constantly coughing, it's going to be hard for you to inhale and exhale because your diaphragm is just going to get tired over time. Has anybody ever coughed a lot? You're just going to get tired of coughing, but you have to. And that is, those are the two toxins I need you to know about and see how they fit into the biochemistry of sympathetic and parasympathetic responses. Any questions? Any questions? Things make sense? Very good, very good. Okay, you all have a great day.